Hello everyone, this is Amit Prambat, your instructor for CS 110 at Laurel Ridge College or VCCS. And today we are going to talk about Chapter 10 for CS 110 operating systems. Let me go ahead and share my screen. So welcome to Chapter 10, Operating Systems. In this chapter, we'll explore one of the most essential components of modern computing, the software that acts as backbone of every device we use. The operating system, or OS, manages hardware, mediates between applications and resources, and ensures everything works together smoothly. Think of it as the conductor of a very complex orchestra. Over the next several slides, we'll uncover how operating systems manage memory, processes, CPU time, and more. By the end, you'll have a clear understanding of the mechanisms that allow computers to multitask, run applications, and appear seamless to the user. Here we outline the first set of goals for this chapter. We begin by examining two core responsibilities of an operating system: managing resources and providing a user interface. We'll explore memory and process management, two areas crucial for efficient computing. You'll also learn how time sharing allows multiple users or programs to feel like they each have their own machine, even though they are sharing hardware. Finally, we'll discuss the difference between logical and physical addresses, as well as compare various memory management techniques used in modern OS design. In the second half of this chapter goals, we expand deeper into memory and process management. First, we'll distinguish between fixed and dynamic partitions, two different ways to carve up the memory. You'll get practice applying partition selection algorithms like first fit, best fit, and worst fit. We'll also explore demand paging, which enables the illusion of near infinite memory using virtual memory. On the process side, we'll learn the stages and transitions of the process lifecycle and study CPU scheduling algorithms that determine how the CPU chooses which processes to run next. By mastering these concepts, we'll understand how operating systems balance performance, fairness, and efficiency. Here, we understand two main categories of software: application software and system software. Application software includes programs we use to solve real-world problems, things like word processors, web browsers, or games. System software, on the other hand, manages the computer at a fundamental level. This includes operating system, file systems, device drivers, and utility programs. The question on the slide asks for examples. For application software, you might name Excel, Spotify, Chrome, etc. For system software, examples include Windows, Mac OS, Linux, and device drivers that allow printers or graphics cards to function. Understanding the difference is key to appreciating where the operating system fits in the software ecosystem. Here we define the operating system as essential system software with three major roles. First, it manages computer resources, things like CPU time, memory space, storage, and input-output devices. Second, it provides an interface for users, allowing us to interact with hardware through graphical interfaces, command lines, or touchscreens. And third, the OS serves as a bridge between applications and hardware, allowing programs to run without needing to know the details of every device. These roles collectively ensure that the system stays organized, secure, and efficient, enabling multiple programs to run smoothly at the same time. Roles of an operating system. Here, we try to understand how an operating system interacts with many aspects of computer systems. The OS acts as a central coordinator between hardware, software, and the user. You can see in the diagram that OS touches nearly every component: memory, CPU, storage, input or output devices, and user interfaces. The slide also asks us what operating systems we have used, and typical examples include Windows, Mac OS, Linux distributions like Ubuntu, and mobile OSs such as iOS or Android. Each of these systems performs the same essential functions: managing resources, running applications, and providing the experiences you interact with. The key takeaway is that the OS is responsible for keeping everything interconnected and functioning smoothly behind the scenes. Here, the central theme is sharing nicely because multiple programs often need the same resources like CPU time, memory, disk access, and peripherals. The OS must ensure fairness, efficiency, and stability. It prevents conflicts by prioritizing tasks, allocating memory carefully, and ensuring that each program gets what it needs while not interfering with others. This is why, for instance, you can stream music, browse web, and update software all at once. The OS enforces rules so that all processes coexist without overloading the system. This resource sharing principle is the foundation of modern computing and enables true multitasking. Here we learn about two core ideas: multi-programming and memory management. Multi-programming means keeping several programs in memory at once so the CPU always has something to work on. This minimizes idle time and increases performance. Memory management, on the other hand, is the process of tracking where each program is stored and how memory is allocated. An OS must make quick decisions such as which programs stay in the memory and how to arrange them efficiently. Without good memory management, programs would clash or overwrite each other, leading to crashes. Together, multiprogramming and memory management ensure that computer can run multiple applications reliably and efficiently. Here we focus on processes, programs in execution, and how the OS handles them. The OS performs process management, which includes tracking what each process is doing, what resources it needs, and its current state. CPU scheduling is part of this. The OS must decide which process gets CPU time next and for how long. Since only one process can execute at the CPU at any moment, scheduling is crucial for fair and efficient multitasking. The OS keeps detailed information about each running task so it can pause one process and run another, and later resume the paused one seamlessly. This creates the illusion that all your programs run simultaneously. Here we look at the early days of computing and batch processing, where there were no operating systems as we know them. Instead, a human operator acted as the OS. They would collect jobs from different users and organize them into batches based on resources required. This reduced setup time and made machines more efficient, but it also meant users waited long periods for the results. The diagram illustrates how operators physically stacked and arranged jobs. While primitive by today's standards, batch processing laid the foundation for automation and scheduling systems in modern operating systems. As computers got faster, the human operator became the bottleneck, paving the way for automated OS-driven job management. Moving on, time sharing. Earlier in the history of OS, there was a concept of time sharing. It was a major development in the history of the operating systems. A time sharing system allows multiple users to interact with computers simultaneously by rapidly switching between tasks. Each user experiences what's called a virtual machine, an illusion that they have exclusive access to the system, even though resources are being shared. This was revolutionary because early systems relied on batch processing, where users submitted jobs and waited. Time sharing eliminated the human operator bottleneck and made computing interactive, leading to the modern multi-user systems we use today. The key takeaway is that time sharing enables fairness, responsiveness, and true multitasking. Other factors such as real-time, response time, and device drivers are being examined here. A real-time system is one in which response time is absolutely critical. These systems run in places like medical equipment, industrial control systems, or automotive safety features, where delays could cause failures. Response time refers to the delay between receiving input and producing a result. The OS must manage resources carefully to guarantee predictable performance. Finally, the slide introduces device drivers, a small program that know exactly how a particular hardware device communicates. Without drivers, the OS wouldn't know how to interact with printers, keyboards, GPUs, or storage devices. These three factors, timing, responsiveness, and hardware compatibility, are essential to building a reliable OS. Memory management. Here we try to understand how the operating system manages memory and translates addresses. Memory management includes tracking where programs are stored and how they are arranged. The OS must convert logical addresses generated by a running program, into physical addresses which refer to actual locations in main memory. This conversion allows each program to operate as if it occupies a clean, continuous block of memory, even if it's scattered across physical RAM. This isolation enhances security and prevents programs from interfering with each other. Understanding the difference between logical and physical addresses is essential to grasping how memory techniques like paging and segmentation work. Here we see how logical addresses are mapped to physical ones. For example, a program might refer to a variable using a logical address such as 23, which is relative to the starting location of that program. Before the program runs, the OS binds this logical address to a specific physical location in RAM. The diagram on the slide shows memory as a continuous series of bits. It's the OS's job to carefully track which range belong to which program. This mapping ensures that each program stays within its allowed memory boundaries, preventing corruption or overwriting. This mechanism forms the basis of safe and structured memory allocation. This slide introduces single contiguous memory management, the simplest memory technique. In this model, only two things exist in memory at a given time, the operating system and one application program. Memory is split into two sections, one for OS and one for the program. While simple, this approach is extremely limited because it allows only one user program to run at once. As computers evolved, this model quickly became insufficient, but it provides a good starting point for understanding more advanced memory management techniques. This diagram shows this simple split, which makes the address translation easy but greatly restricts multitasking. Here we see how logical and physical addresses work under single contiguous memory management. A logical address is simply an integer that represents the position relative to the program start. To convert it to a physical address, the OS adds the logical address to the starting location where the program was loaded in memory. This makes translation straightforward because each program occupies one continuous block. While easy to implement, this technique wastes memory and limits flexibility because only one program can run at a time. Nevertheless, it provides an important foundation for understanding later methods like partitioning and paging. Here we see a concrete example of address binding. If location represents physical address 100 and logical address of sum is 23, then the physical address is 100 plus 23 is 123. The diagram illustrates how simple this process is in a single contiguous memory system. This ease of translation is one of the strengths of the model, but as noted earlier, it doesn't scale well to systems running multiple programs. This limitation is why more flexible techniques like fixed and dynamic partitioning were developed. Still, understanding simple binding prepares us to understand more sophisticated address resolution methods. Here we understand partition memory management. This expands beyond the single program limitation. In partition memory management, memory is divided into multiple partitions so that the OS and several programs can coexist with RAM. Two approaches exist here: fixed partition and dynamic partitions. Fixed partitions divide memory into predetermined blocks, while dynamic partitions create partitions on the fly to fit program sizes. This allows multiple programs to be loaded, improving system throughput and resource usage. The main challenge becomes deciding how to divide memory and which program goes where, setting the stage for partition allocation algorithms. Here we understand how OS handles address resolution in partitioned memory environment. Each program resides in its own partition, and two special registers are used to ensure memory safety: the base register and the bounce register. The base register stores the physical starting address of the program's partition, while the bounce register stores the size of that partition. When a program accesses memory, the OS checks whether the logical address falls within the partition's limits. If it does not, the access is blocked to prevent memory violations. This safeguard ensures programs cannot interfere with each other, which is a critical feature of multitasking. Here, this slide highlights why it's essential to check memory accesses in a partition systems. The OS must ensure that every logical address stays within range allowed by its partition. The diagram shows how logical addresses are translated using the base and bounce registers. Without these checks, programs could accidentally or intentionally access memory belonging to other programs or even the OS, causing crashes or security breaches. Memory protection is therefore a core responsibility of the OS. Partitioning provides better multiprogramming support than single contiguous memory, but it still requires careful monitoring to remain safe and efficient. Partition selection algorithms. Oh, let me get back to the slide again. Okay. So there are three key partition selection algorithms: first fit, best fit, and worst fit. First fit selects the first available partition that is large enough, making it fast and simple. Best fit chooses the smallest partition that can hold the program, which minimizes the wasted space, but may require scanning more memory. Worst fit selects the largest available partition, attempting to leave reasonably sized leftover blocks. This slide asks for rationale. First fit is efficient, best fit minimizes internal fragmentation, worst fit attempts to avoid many tiny usable fragments. Each strategy has trade-offs, and no single algorithm works best for all workloads. This slide provides practice of using partition allocation algorithms. We are given 6 blocks of sizes 1000, 700, 750, 1500, 300, and 350, and 5 request sizes. If we apply each request independently using first fit, we match the first block large enough, 1000 to A, 25 to A, 780 to independently using first fit. We match the first block large enough and 1600 to none, 325 to F, etc. For best fit, we choose the smallest possible block, such as 1000 to A, 25 to E, 780 to D, 1600 to none, and 325 to F. And for the worst fit, we choose the largest available block, 1000 to D, 25 to D, 780 to D, 1600 to none, and 325 to D. This slide illustrates how algorithm choice affects memory allocation. Paged memory management. It divides processes into fixed size pages and divides main memory into frames of equal size. A frame holds exactly one page. This allows process to be scattered across memory rather than occupying single continuous block. Paging solves fragmentation issues and makes memory allocation flexible. The OS keeps a page map table for each program to track where its pages reside. This system is essential to modern computing because it enables efficient multitasking, relocatable memory use, and simpler address translation. If program 1 needs logical address 2566, the OS must determine which physical frame holds the corresponding page. The page number and offset within the page are calculated based on page size. Once the page number is known, the OS checks the program's page map table to locate the correct frame in memory. This demonstrates how paging allows programs to access memory even when their pages are scattered throughout RAM. Now, here we walk through logical address translation. To map a logical address to a page number and offset, divide the address by the page size. Here 1024, so 2566 divided by 1024 equals page number 2, and then remainder 518 is the offset within the page. The OS then uses this pair to 518 to determine where the data physically resides. This standardized approach works regardless of where the page is stored in memory, making it essential for flexible memory allocation. Here the slide shows how 2518 becomes a physical address. The OS looks up page 2 in the page map table to find which frame contains it. Suppose page 2 is stored in frame X. The physical address is the starting address of frame X plus offset 518. This two-step lookup, logical to page, then page to frame, is the foundation of paging. It enables safe memory sharing, relocation, and protection, all central features of modern OS design. Here we learn about demand paging. Instead of loading all pages of a process into a memory, the OS loads pages only when they are needed. If a page is not currently in memory, the page fault occurs and the OS retrieves it from secondary storages. Sometimes it must swap a page out to make room. This is called a page swap. Demand paging makes programs appear much larger than physical memory, enabling virtual memory systems and allowing efficient multitasking. But excessive swapping can slow the system. Virtual memory allows processes to run regardless of their size relative to physical RAM. Only the necessary pages are loaded, creating the illusion of abundant memory. However, heavy swapping, called thrashing, occurs when the OS spends more time moving pages in and out than running programs. The slide asks how all computing is a trade-off relates. Virtual memory increases flexibility and capacity, but the trade-off is potential performance loss during high paging activity. The coordination of all process competing for the CPU time is what is called a process management. The OS must track each process's state, manage transitions, and allocate resources. Here the slide asks, what stages does process go through? The key stages are new, ready, running, waiting, and terminated. These states describe the life cycle of programs as it moves through the system from start to finish. Here we see process lifecycle example. A process moves to the waiting state when it needs something external like I/O before it can continue. For example, reading from disk on waiting for user input, the diagram shows how processes move between states based on events such as CPU scheduling, I/O completion, and interrupts. Understanding these transitions is essential for studying how OS keeps the CPU busy and resolves competition among programs. Here, the slide introduces process control block or PCB. The PCB stores all information OS needs to manage a process. Its program counter, CPU register values, memory limits, and accounting data. Each state, ready, waiting, etc., has its own list of PCBs. When a process changes state, its PCB is moved between these lists. The PCB is the OS's control center for tracking every active process. Here we understand context switching. Because the CPU can only run one process at a time, the OS must save the current process's register value into the PCB before switching. Then it loads the next process's values from its PCB into the CPU. This exchange allows processes to pause and resume smoothly. Although necessary, context switching has overhead, so efficient scheduling aims to minimize excessive switching. You may pause the slide and read through the different state the process moves into. Moving on to CPU scheduling. Here we introduce CPU scheduling, the process of deciding which ready process should run next. With many processes waiting, the OS must choose the one that best satisfies goals such as fairness, efficiency, and responsiveness. The slide asks which one gets to move from ready to running. The answer depends on scheduling algorithm being applied, such as first come, first serve, or shortest job next. Here, the slide distinguishes non-preemptive and preemptive scheduling. In non-preemptive scheduling, a process gives up CPU only voluntarily, such as when it finishes or waits for I/O. In preemptive scheduling, the OS can interrupt a running process to give another process a turn. Turnaround time, the time from job arrival to completion, is used to measure performance. Preemptive methods tend to improve responsiveness in multitasking environments. There are three major scheduling algorithms. First come, first serve runs processes in arrival in order. Simple but potentially inefficient. Shortest job next chooses the process with the shortest estimated running time, optimizing average turnaround time, but requiring good time estimates. And round robin gives each process a fixed time slice, improving fairness and responsiveness. These algorithms illustrate trade-offs between efficiency and fairness. Here's an example of first come, first serve. We can also call it FCFS scheduling scenario. And it's asking for average turnaround time. Under FCFS, processes run in an exact order they arrive. To compute turnaround time, you add waiting time plus execution time for each process, then average across all processes. FCFS can lead to the convoy effect, where one long process delays all shorter ones, increasing average turnaround time. Shortest job next example. The OS always selects the shortest available job. To calculate average turnaround time, you schedule processes by increasing duration, compute finish times, and average them. SJN typically produces better average turnaround time than FCFS, but requires predicting job lengths, which is not always possible. Round robin scheduling. Each process receives a time slice or quantum of CPU time. If it doesn't finish, it returns to the ready queue to wait for another turn. This ensures fair access to the CPU and prevents any single process from monopolizing resources. Round robin is widely used in multitasking systems because it provides good responsiveness. Here the slide presents round robin example with a time slice of 50. To compute average turnaround time, simulate the time slices in order, tracking when each process completes. Round robin may produce longer total turnaround times compared to SJN, but it ensures consistent interaction and fairness for users, critical in interactive systems. CPU scheduling algorithms. So here the slide asks if algorithms are preemptive or non-preemptive. First come, first serve is a non-preemptive because the running process stays until it finishes or blocks. Shortest job next is typically non-preemptive unless they extend it to SRTF. Round robin is preemptive because processes are forcibly paused after each time slice. Understanding these distinctions helps explain how the OS maintains fairness and responsiveness. Ethical issues. The slide focuses on ethical and legal implications of HIPAA, the Health Insurance Portability and Accountability Act. The goal of HIPAA is to protect sensitive patient health information from being disclosed without consent, ensuring both privacy and security. You have likely signed a HIPAA form at doctor's office. These forms explain how your medical data can be used and shared. The slide asks what de-identified information means. This refers to patient data stripped of personal identifiers such as name, address, social security number, or anything that could directly trace the information back to the individual. The benefits of HIPAA include stronger privacy protections and more standardized healthcare practices. However, challenges include complexity of compliances and limitations on data sharing for research. As technology evolves, maintaining privacy while enabling innovation continues to be a delicate balance. Well, here's a fun historical clue. I will always be associated with a garage and a fruit refers to Steve Jobs, co-founder of Apple. The garage references the famous story of Apple beginning in Jobs' family garage, while the fruit is, of course, Apple Inc. The slide also asked why he was in the news in 2011. That year marked the passing of Steve Jobs, who died on October 5th, 2011, prompting worldwide coverage and tributes. His influence on personal computing, smartphones, and digital media remains profound, and his legacy continues to shape modern technology culture. Here are several interesting tech-related questions. Black Ross is known for co-creating Firefox web browser at a young age. He later worked at Facebook and retired early, with his net worth widely reported as several million dollars. Another question asks about the most influential computing job of early 1960s. Many historians point to positions in mainframe operation and early programming roles, which were crucial to as a computer first entered business and government. Next, the slide asks if Bitcoin is a currency. The ongoing debate centers on whether it functions as money, an asset, or a decentralized digital commodity. Then, your sneakers talk to your iPod refers to early wearable fitness sensors like Nike plus iPod system. Finally, the question about ejecting flash drives but unplugging phones relates to data writing behavior. Flash drives can lose data if removed during writing, while phones use safer transfer protocols. These questions spark curiosity about how technology evolves and integrates into our daily lives. Thank you for joining the session today. I hope to see you in the next session. Take care.